Hi there, I'm Maria at RedShiftBio. RedShiftBio is an energetic company with an exciting new technology that leads us to the future of biopharma development, where decisions can be made easier with more confidence. This technology is microfluidic modulation spectroscopy, or MMS. It measures previously undetectable structural changes in biomolecules. With its groundbreaking precision and sensitivity, it now allows us to understand what we previously don't understand, quantify subtle differences, and ensure the best quality of our products. I have been noticing that the same protein, same concentration, but in different buffers have subtle structure differences. So here I've got an alpha-helix rich protein, lysozyme. And then I have water, I have PBS, phosphate buffer, and trace buffer. And then I've made a 10 mg per ml lysozyme in water, in PBS, in phosphate buffer, and in trace buffer. Now, let's go and take some MMS measurements. Next, I simply loaded the samples and buffers into a wall plate and logged it into the system. The rest of MMS measurements is a quick start. Now, let's look at the results.
We first take the second derivative of the protein molecule's absolute spectrum to see the characteristic peaks. Then we will have multiple ways to better visualize and quantify the differences. Now let's follow the first row and look at the second derivative and the delta of the second derivative. Here I have color-coded the wave number range for different motifs. From left to right is intermolecular beta sheets, turn, alpha helix, unordered, intramolecular beta sheets, and intermolecular beta sheets again. Lysozyme, as an alpha helix rich protein, has a strong peak around 1657. This peak is the lowest in water and gets stronger in PBS than phosphate buffer and the strongest in trace buffer. A similar trend also appeared around 1676. The delta plot on the right makes the differences more obvious. Here, all the curves are compared to the average of the lysozyme in water. The three replicates of lysozyme in water are fluctuating within the dotted lines. Lysozyme in PBS, phosphate buffer, and trace all deviate from lysozyme in water, with PBS deviates the least and trace deviates the most, especially at the 1657 and 1676 peaks. Next, let's follow the second row. The similarity curve is basically a flip over of the second derivative curve. Here, instead of looking at the characteristic wave numbers, we are quantifying the overall structural similarity or differences. On the left side, we use area of overlap, or AO, to quantify the overall structural similarity. The table has side-by-side the repeatability and the similarity score between samples. We see that the repeatability within the same sample is above 99%, and the overall lysozyme structural similarities in buffer as compared to water are 92% for trace, 94% for phosphate buffer, and 96% for PBS. On the right side, we use weighted spectral differences, or WSD, to quantify the overall structural differences. In the table, the WSDs of lysozyme in buffer as compared to water are much greater than the repeatability among replicates. And again, the overall structure of lysozyme has the most difference in trace, followed by phosphate buffer, then PBS. Last, following the arrow in the second row, we can use multiple Gaussian curves to fit the spectrum to further calculate the percentages of each secondary structure motif composition. Here is the higher order structural motif composition bar chart. The alpha helix composition in lysozyme is increasing from water to PBS, then to phosphate buffer to trace. Finally, to summarize, MMS can detect and quantify subtle buffer-induced structural changes, which is previously very challenging to be experimentally quantified. With this information, MMS can help you choose the best formulation to maintain the optimal structure. The result also demonstrates the importance of measuring protein in the formulation of interest, since changing buffer or diluting buffer would result in structural changes.
Thanks for sticking to the end of the video. Please consider giving us a thumbs up.